We're going to continue on in Chapter 12, covering sections 3 through 5 in this lecture. So we're going to start with entropy and structure. Entropy is affected by mass, molecular structure, mass distribution, and rigidity. Think of freedom of motion, how much they can move. So the standard molar entropies of molecular substances is linked to this mass and their structures, as well as the distribution and rigidity. The quantities of energy involved in rotational motion, it depends on how massive the molecules are and on how their masses are distributed. So, for example, if we look at octane and tetramethylbutane here, look at how their masses are distributed. Consider the entropy values of octane and tetramethylbutane. These both have the same molar masses, and we're looking at them at the same temperature. But when the mass of the molecule is more spread out, like it is in octane, so we have this, this long chain here, the spacing between its rotational energy states becomes smaller, and more microstates are accessible. So therefore, the molecules of octane are going to have a greater entropy than the same number of molecules of tetramethylbutane at the same temperature. Another structural feature that we find that influences entropy is called rigidity. And the two most common forms of carbon happen to be a diamond and graphite, like you would find in a pencil. So the diamond is an extremely hard substance because it has a rigid three-dimensional atomic structure. And its atoms have access to fewer microstates, which means it has less entropy. It has 2.4 joules compared to graphite of 5.7 joules. The atoms in the graphite are soft and easily deformed, and they have graphite is in sheets, and so when you write on paper, it's that graphite that comes off onto the sheets, which is how pencils work. So another example, going back over here, we're thinking about freedom of motion. If we were to build these models, you would see that you can't twist tetramethylbutane around. You cannot twist any other way other than the way it is right here. But the octane has more conformations that it can twist into. Also, we need to think about solids, liquids, and gas. So the entropy of a solid is going to be less than the entropy of a liquid. It should be liquid, which is less than the entropy of a gas, which would be the highest entropy. Because the gas has more freedom of movement and higher entropy than the liquid has more freedom of movement than a solid would have. So 3 things that can cause entropy to increase. And I'll just write them, I guess, across here. 1, an increase in temperature because the atoms move faster. 2, an increase in volume, more area to move around. And 3, when the number of independent particles are increased. So an increase in the number of particles. All 3 of these allow more freedom of movement. So we have learned enthalpy, heat content. But now we need to determine spontaneously or not. Very slow can still be spontaneous. So thermodynamics predicts whether a process will occur spontaneously on its own without adding anything to it. Non-spontaneous processes, we have to do something to make them go. We have to put energy in. So, but the really important takeaway on this particular slide is this right here. Spontaneity does not equate to being fast or slow. Very slow is still spontaneous. Very fast, still spontaneous. So this is an energy diagram, and in an energy diagram we have energy on the y-axis and reaction of the progress on the x-axis. So thermodynamics, initial and final states, spontaneous in the shaded area here. So if for this one, the reactants are lower than the products, so this would be an endothermic process, and it needs to get over this hump to start making products. This is called, that would be called activation energy. Later on, we're going to talk about kinetics, and that's going to talk about the speed. So again, we're not really discussing the speed at this point, only do they proceed or do they not proceed. So any spontaneous process will be non-spontaneous in the reverse direction. I know I mentioned in an earlier lecture about, rust is spontaneous, but the car doesn't go back to not being rust anymore. It doesn't go from iron rust to iron metal. It goes from iron metal to rust spontaneously. So the reverse of that would be non-spontaneous. Spontaneous process occurs because they release energy from the system, and most spontaneous processes proceed from higher potential energy to lower potential because they're more stable at the lower potential, and that's called exothermic. However, there are some spontaneous processes that do proceed from lower potential to higher potential, an endothermic process. How can something absorb potential energy yet have a net release of energy? So the missing piece of that puzzle is called entropy, because a favorable entropy is actually more important than an unfavorable enthalpy. So we want a favorable entropy is more important than an unfavorable enthalpy. So melting ice still requires input of heat energy, endothermic. So why is melting ice spontaneous? Well, ice will melt spontaneous as long as the temperature is above 0 degrees Celsius. But remember, melting is endothermic, so it has a positive delta H, which is unfavorable, but a favorable entropy is more important than an unfavorable enthalpy. So for ice, we would have a positive delta H and a positive entropy, delta S. Because entropy, packed molecules, so in ice, we're going from a solid to a liquid. So those packed molecules to a liquid allows more freedom of motion. So when solids melt, the particles have more freedom of movement, and when systems have more freedom of motion, energy is released. And that energy that gets released is what we call entropy. Water evaporating is endothermic yet spontaneous for the same reasons again. It's going to have a positive delta H, which is not favorable. It's going to have positive enthalpy, but it's also going to have positive entropy because it's going from less freedom of motion to more freedom of motion. So that favors the entropy, more in the gas phase than in the liquid phase. Salt dissolving in water is spontaneous. Again, it's the same answer. Freedom of what? Freedom of movement. It's going from a solid form to what we call an aqueous form. And aqueous just means it's been dissolved in water. And we know when we dissolve salt into water, it breaks into its respective ions, the chlorine ions and the sodium ions. And they're surrounded by a sphere of water molecules. The intermolecular forces, we call this, is ion dipole. and it does allow for more freedom of movement for the sodium chloride in this state, which is why, again, it would be favorably spontaneous. Higher entropy of a subject or a substance increases when solid becomes a liquid and when liquid becomes a gas. So remember, it's in the solids has less entropy than the liquids, has less entropy than the gas. Least amount of movement, most amount of movement. And you can see that in this diagram over here. So this is the three ways, that we can increase entropy. And entropy will also increase when when a solute dissolves, such as sodium chloride, or if we increase the temperature. So let's talk about favorable entropy. We did some calculations in the last lecture for entropy, so we're going to do a little bit more now, a little bit different. The entropy change for a reaction can be written as an equation like this, and you've seen this equation before, where N and M are the coefficients of the products and the reactants. We saw this when we did enthalpy, so remember, just putting an H in there. We did this for enthalpy as well. It's the same equation, but now we're going to do it with entropy. Entropy for the free elements in their standard states is not zero. So remember, for delta H, we had the hydrogen gas and the nitrogen gas and the oxygen gas and fluorine gas and chlorine and bromine and iodine. These were all zero for delta H. They are not zero for the entropy. You also need to keep in mind that a favorable entropy is positive and a favorable delta H is negative as we move forward. Some applications of the second law, and I think this is another little mini review here because I think we've talked about this before. The change in the entropy of the universe is equal to the change in the entropy of the system plus the change in the entropy of the surroundings. Both of these, one or both of these, has to be temperature dependent. So if delta S is greater than zero, in other words, a positive delta S, then the system is spontaneous. So if we have water, liquid, and water gas, we can look at this because gas is more chaotic than liquid. So temperature has an effect on spontaneity because delta S being positive or negative. So at a lower temperature, let's look at how temperature does affect this. So at a lower temperature, so if temperature is between 0 and 100 degrees Celsius, then the spontaneity is going to lie to the left because it's going to be mostly liquid form. And delta S would lie to the left here. However, if the temperature is really high, so if we have a temperature greater than 100 degrees Celsius, then we're going to have mostly gas present. And so the spontaneity is going to we say it's going to lie to the right of the equation. It's just a way of looking at these. Another example here, the combustion of natural gas has a delta H around negative 890 joules. So we want to look at what's happening with the spontaneity here. The thing that we can look at here is we can look at how many moles of gas to how many moles of gas on each side. So over here we have 1 plus 2. That gives us 3 moles of gas over here. Over here we have 1. This is liquid. So 3 moles of gas to 1 mole of gas plus 2 moles of liquid. So because of this, it goes to fewer degrees of freedom on the product side. So the reaction is spontaneous because there is a decrease in entropy. If we have a positive entropy, then the sum of the system and the surroundings must be greater than 0. So remember, our equation was delta S of the universe equals delta S of the system plus delta S of the surroundings. So if positive delta S, then the sum of these must equal something greater than 0. If the system is a negative or less than 0 for delta S, then the system of the surrounding must be greater than 0 and large enough to offset the value of the delta S of the system. So it all just works out mathematically, actually. In the previous one, the system was cooler than the surroundings. So let's do one where the surrounding is cooler than the system. So now energy is going to flow from liquid water to the freezer. So the water is our system, and the freezer is the surrounding. So first we'll calculate delta S of the system. So delta S of the system is going to be a negative Q of the system because it's flowing out over temperature. So that's going to be equal to 1.00 moles times the negative 6.01 times 10 to the 3 joules per mole. That is still the same value from our previous slide. We're still working with water. And this is at 0 degrees, so over 273 Kelvin. So that's a negative 22.0 joules per Kelvin. Then the delta S of the surroundings, which is colder. Remember, it flows from warmer to colder. So this is going to be a positive Q of the surrounding divided by the temperature. So this is going to be 1.00 moles times a positive 6.01 times 10 to the 3 joules per mole divided by, this is a negative 10, so that's going to be equal to 263 Kelvin. And that's going to give me 22.9 joules per Kelvin. So now I'm going to add it up again, just like I did for the last one, system of the universe. That is equal to the delta S of the system, which is negative 22.0 joules per Kelvin, plus the sum of the surrounding, which is a positive 22.9 joules per Kelvin. So this one, we're going to get a much smaller, it's still going to be positive, but it's going to be much smaller. It's only 0.9 joules per Kelvin for delta S of the universe. So we still get an increase in the delta S of the universe, even if it's flowing in the opposite way there. So a second way to calculate entropy changes. So we've been calculating with just, a straightforward equation, but there's a second way, and we talked about this just a little bit earlier. We pointed out that this is the same equation that you used for enthalpy, delta H of reaction. So just, you put H in there as well. The only difference is now your diatomics are not 0. So be careful of that. So now you're going to have values for everything. And again, this would be things that you would be given values for. It's not something that you're expected to know. So let's do an example. Yes, let's do the example on the next page, I think. No, I've been writing an example on this page. Change my mind. Okay, let's do another example. So we have CH3OH gas, a hydrocarbon, and water is gas water, so it's vapor, and CO2 gas, and that gives us the CO2 and the H2 gas. And so you would be given the values of S. Now, your values of S is in units of joules per mole per Kelvin. On the last slides, we got rid of mole because to make our adding easier. We just did it for 1 mole of each. But now we have different moles. So we have 3 moles of hydrogen gas and 1 mole of this and 1 mole of this and 1 mole of this. So we are not going to get rid of moles. The moles is now the coefficient of the reactants. So writing these out in this format, I can get the delta X of reaction, there should be a little 0 there. It's going to be equal to the summation of the products. So I'm going to go over here first. I have 1 carbon dioxide, and carbon dioxide is 213.8, and these are all in units of joules per mole per Kelvin. Plus, I have 3 waters, or sorry, hydrogen gas. So 3 times 130.6. And it's the products minus the reactants. So on the reactant side, for CH3OH, my S value is 239.9. And for H2O, my S value is 188.8. So adding these up, I get, for my products, I get 605.6 joules per mole per Kelvin minus 428.7 joules per mole per Kelvin. So that gives me a delta S of the reaction equal to 176.9 joules per mole per Kelvin. And it is a positive delta S. So that means this is exothermic and spontaneous. Let's look at another one. So for this one, you're going to do the same thing. You're going to take 4 of the carbon dioxides and 6 of the waters. That's your products. And then for the reactants, you're going to have 2, and you're going to have 7 of the oxygen. So see, the diatomics are not 0 anymore, and these are your reactants. And then it's going to be the products minus the reactants. This is shown on the next slide. So we did just that. We took the 4 times the carbon dioxide, the 6 times the water, minus 2 times the hydrocarbon, plus 7 times the oxygen. And when we did that, we got a delta S equal to negative 620.2 joules per moles per Kelvin. So, this is actually the one that we worked out earlier. That's good. So you can try to work the same one out that we worked out earlier. Again, it's going to be the products minus the reactants. And I will see you in class. Have a good day.